In this video, we're going to be looking at data in various forms. Now, we're going to say in this example, we have a tree. Now, the tree wasn't planted this year, but it was planted the year before. And let's take a look at our axis right here. So we're actually going to start our clock in April. So this right here, 0, 0 time is the beginning of April. So this is April, May, June, July, August. And trees typically only grow from April to August, and then they kind of start to just kind of mellow out in the fall. So this tree right here, this tree in the beginning of April at time 0 was 1, 2, 3, 4, only 4 inches tall. It's a sapling, it's a seedling. It's very small. So we're going to be looking at equations and slopes and point-intercept forms. So you may remember from your algebra class that the equation of a line is always simply y equals mx plus b. Pretty simple, right? So you remember that m is the slope, x is the independent variable, and b is the y-intercept. Okay, so let's write the equation of this line. So y, we're going to write the equation of the line with no units, just very generically. So y equals, let's take a look at the slope. It rises 1 and goes over 1. Rises 1, goes over 1. Rises 1, goes over 1. So the slope is simply, well, 1. I don't really need to write 1, but I'm just trying to emphasize that. 1x. And the intercept is 1, 2, 3, 4. The intercept is really just, well, 4. So there is your line. Y equals 1x plus 4. But here is the thing. We can't simply write this in a class like physics. We need to express it with units because units are so important because units tell us what we're talking about. So I'm just going to rename these variables from a very, very generic y, from a very, very generic x, and I'm going to be adding units. So y, instead of y, now look at the y-axis right here. It's height. So instead of calling it the y-axis, I'm going to be calling it the height axis. So I think it would make sense to abbreviate height as h. So the height of the tree equals, now we know the tree is growing 1 inch per month. It's kind of a slow growing tree. So we're still going to have the 1. We're still going to have the 1 right here. But what's important here are the units. How much does the tree grow per month? Well, it goes 1 inch per month. So take a look at this. It grows 1 inch per month, right? It rises inches and runs months. So that is the unit of the slope. So right here we have inches per month, if you can read that. Okay, 1 inch per month. Now, we're also going to rename this very generic x. Instead of saying x, we're going to be saying, it's time. And I think it's appropriate to abbreviate time with t, right? Right here, so t. Now, plus the y-intercept. It's still 4, right? The number doesn't change, but we need our units. So for what? Well, look at the y-axis. It's 1, 2, 3, 4, 1, 2, 3, 4, but 4 inches. So that is our unit here, 4 inches. So I should have just abbreviated that inch. There we go. So there is your equation of the line right here. So here's your equation of the line. So this expression right here, this equation right here represents the equation of the line with units. So let's kind of make sure we really understand what this is. we simply do not want to write generic math equations. We have to put it in what I like to call physics form because the units are very important to what we describe. So take a look right here. So let's get the marker tool right here. Okie doke. So we have, oops, wrong tool again. Try again. Okay, this right here. So every month, the tree grows 1 inch, right? The tree starts at 4 inches, but every month it grows 1 inch. So as every month goes by, it grows another inch, and another inch, and another inch. So if there was no such thing as fall or winter and it was perpetual spring and summer, the tree would just continually grow pretty much forever. But the graph would, of course, stop as winter would proceed. So this is simply what we need to do in this class. We can't just express basic generic equations. We have to have units, because the units describe things. The units describe like how things are changing or what they are, etc., etc., etc. Now, to be a little bit more directly related to physics, so let's say we have right here, we have our cat, So let's say the cat goes from 7 meters to -1 meters. I could have actually extended the graph a little bit. Okay, so that's -1. There we go. So the cat starts at 7 meters and goes to -1 meters. So we have this number line. So we have this graph. Here's one way to represent, the position. The position of the cat is a graph, right? So position versus time. Time is very typical on the x-axis. You almost never see time on the y-axis. Now, we have to look at our position number line, which is right here. Well, we need to define where the origin is. So I'm going to say that this right here is 0 meters. And I'm going to draw the origin the best I can. The arrows, kind of small, but you can kind of see it. Now, the cat Tucks the cat starts at 7 meters. So 1, 2, 3, 4, 5, 6, 7. Okay. So the cat, it's like running across the room or something. He's running to his meow-mix. He's running from 7 meters to -1 meter. So as time is going by, the cat is moving to the left and ends at -1 meters. Okay? Now we can write the equation of this line. The equation of this line is pretty simple. So again, let's start off very generically. Y equals mx plus b. Well, let's take a look at the slope. The rise, I know it's kind of weird to say rise when it's going down, but the rise goes down 2 over 1, down 2 over 1, down 2 over 1. So the slope is simply -2. Well, x is still x, and the cat starts at 7. So here we go. So this equation right here, this is a very generic, equation of the line, but that's not good enough. We need to express this in terms of units. We need to tailor the equation, to fit our situation. So this is going to seem a little counterintuitive, but see the y here? Let's use the laser. See the y? Now, the position of the cat, oops, wrong tool. The position of the cat, he's in the X, he's not going, he doesn't have a jetpack. He's not flying up and down. That would be wicked cool though. The cat is moving left or right. That's the X direction. So for the X direction, we're going to use, well, the letter X. So I know it's kind of strange to call this y-axis, X, but we actually use the letter X for horizontal position in the X direction. A little redundant to say that, but I just want to drive that point. So we have x. Now, how fast? What is the slope of the situation? Well, it's still -2. Now, notice I put in parentheses here. I just do that to keep the math clean and to focus on the units. So -2 what? And that's what you must always ask yourself. I mean, basically every number in physics has a unit, almost without exception, almost. So the cat goes down, -2 meters over seconds. So the rise is meters, and the run is seconds. Let's take a look at this. The slope is down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. And the units of the slope, it goes down meters, right? It goes down meters and runs seconds. So meters per second, You can kind of see it in the title too, position versus time. Okay. Now, instead of saying x, the x-axis is time, and it seems very appropriate to abbreviate time with the letter t. And also, the cat starts at 7, but 7 what? 7 meters. So we're still going to write 7, but 7 meters. So I just want you to kind of see the progression. We start off very generically with a point-intercept form. We write the very generic equation of the line, but we tailor the equation. We tailor the equation with physics. So you shouldn't just leave it in general form. It has to be tailored. So this equation right here, I can just highlight it. See right here, this equation right here, that describes the position of the cat at all times. So if I wanted to, if I plugged in, oops, shouldn't do that. If I plugged in for t, let's say I plugged in, say, 2 seconds, right? If I plugged in 2 seconds here, well, it would tell me where the cat is. So -2 times 2 is -4. -4 plus 7 that's going to be 3. And if you look at the graph right here, it's 3, right? So what we're going to be doing in physics is when we're examining data, it's simply not good enough to write a generic, point-intercept form expression. We need to tailor it with units. And you do that by looking at the graph. That's why it's so important when you make your graphs to properly label them with your units, because really you're just getting all this information out of the graph. The slope is -2, but -2 meters per second. So we will be doing more examples of this in the future, and I'll see you in the next video.